Now, if I make some lemonade and I give it to my son and he says, the lemonade's too strong. I mean, he wouldn't, because who would ever say that about lemonade? Well, let's just say that he does. He says the lemonade is too strong. That means that it's too concentrated, right? I've added too much of the lemonade mix to the water, so the solution has become very, very concentrated. And if I give it to him and he says, that's too weak. It's too weak, Dad. Add more sugar. Add more stuff to it. If he says that it's too weak, then he means that it's not concentrated enough. And those ideas would make sense in our everyday language. However, when we're dealing with acids and bases, the terms strong and weak get applied a bit differently. So what is a strong versus a weak acid, or a strong versus a weak base, and how is that different than concentrated or dilute? So let's start with a strong acid. So what does it mean to be a strong acid? One example of a strong acid is nitric acid, HNO3. And we know from the Arrhenius definition of acids and bases that an acid is something that if we add it to water, it's going to react with the water molecules to form hydronium, H3O+, and some kind of leftover bit here. So my nitrate ion that would be floating around, right? That's what makes this thing an acid. Now, what makes it a strong acid? Strong acids are acids that when I add them to water, so imagine that I have my nitric acid in a beaker here and I'm adding it to water. When I add it to the water, all of these HNO3s enter the water. And because it's a strong acid, it means that they are all going to react with water molecules to form hydronium, or at least more than 99% of them are going to react with water molecules to form hydronium. So we can see that happening here. This one would react to form a hydronium. So I've got one hydronium. This one's going to react to form another hydronium. This one's going to react to form another hydronium. This one's going to react to form another hydronium. The strong acid has a hydrogen ion that was not very strongly held to this other negatively charged bit. So the water in the solution is able to break it apart easily, and I form lots of hydronium, right? All of these HNO3s have reacted to form hydronium. So in my example here, where I've got HNO3, aqueous, we know from modified Arrhenius that it would react with water, and this hydrogen here gets transferred to the water to form hydronium. So the way that we can specify that this is a strong acid is we say this reacts greater than 99%. And we can put that over the arrow, which is going to specify that this reaction is essentially quantitative. Quantitative means that it goes 100%. Sometimes we might use this kind of notation instead. We would say essentially 100%. There are 6 common strong acids that you should recognize as strong acids. So we have sulfuric acid, H2SO4, nitric acid that we were just looking at, hydrochloric acid, HCl, hydrobromic acid, hydroiodic acid, and perchloric acid. Those would all be examples of strong acids. Now, what about a weak acid? Acetic acid is a weak acid. It's the active component of vinegar. And the thing that makes it weak isn't that there's necessarily less of the original acid, but it's that when it's added to water, not all of these acetic acid molecules are going to react to produce hydronium. So if I have 4 here and I add them all to water, because the hydrogen ion and the acetate over here are held more strongly together, for many of these, the hold between these is too strong. The water molecule can't pull the hydrogen ion away to form a hydronium. So for maybe one of these 4, it will react to produce a hydronium, but for the other ones, they won't. So even though I still started with 4 molecules of my original acid, only one of them reacted to form hydronium. So the concentration of hydronium ions in my resulting solution is a lot less. It's only 1 molecule of hydronium per my beaker versus the 4 we had before. And remember that the hydronium ions are the things that make the solution acidic. So even though these are both acids, because the acetic acid is a weak acid, it produces less hydronium in the solution, it's going to have a more neutral pH. The pH is going to be closer to 7 than for the nitric acid, the strong acid, because this guy produces less hydronium. And so we would denote this by writing a less than 50% over the reaction arrow, because my weak acid reacts with water less than 50%. So mostly it's going to be these original reactants left in the solution instead of forming these products. Acetic acid actually only reacts at about 1%. So if I add 100 acetic acid molecules, CH3COOH molecules to the solution, only maybe one of them is actually going to react with water to form hydronium. The same idea applies to bases. Strong bases are ones which dissociate 100% in solution. So 100% of the original base is now turned into hydroxide ions. Weak bases react incompletely, just like the weak acid did. Ammonia and the hydrogen carbonate ion are both examples of weak bases. We need the modified Arrhenius definition to explain them. When they react with water to produce hydroxide, they do so less than 50%, often much less than 50%. So very few of these original molecules form hydroxide, which means there will be less hydroxide in solution. But what about the terms concentrated and dilute? Does this mean that they don't apply to acids and bases? No, they do, and they can be used at the same time as strong and weak. So we have to make sure that we're keeping track of the difference. If I have a concentrated strong acid, that means the concentrated bit means that I'm adding lots of the acid to the solution, right? I'm adding a whole bunch of acid to solution. The fact that it's strong means that each of these guys is going to react and form hydronium. I could have a dilute strong acid, and that's what I would get if I only added a little bit of the strong acid. So even though I've only added one of my 4, I haven't added very much of this nitric acid. It is dilute, but it's still a strong acid because of this one molecule that I did add. It is going to go and react to form hydronium. That's what makes it a strong acid. The nitric acid here is always going to be a strong acid, no matter if I add 1 drop to a swimming pool or if I add a truckload to a bathtub. It is a strong acid in either of those cases. And likewise with my weak acid, my acetic acid is always a weak acid. If I add only a little bit of acetic acid to solution, then it's a dilute weak acid, meaning less than 50% of the acid that I'm going to add is going to go and do this. So if I only add 1 molecule, chances are it's just going to stay together. But I can also have a concentrated weak acid. If I add a lot of weak acid, then it is concentrated. I've got a high amount of my original acid particles. But this is a weak acid. So like we said before, only some of those are going to react to form hydronium. Most of them are going to stay together. And so for the acetic acid too, it is always a weak acid, regardless of whether I add a teaspoon to a swimming pool or a truckload to a bathtub. In both of those cases, it's a weak acid. The difference is whether it's concentrated or dilute.